So let's take a couple minutes to write down some properties of mutual information. Okay, so first off, we just saw this. Well, let's first write down the definition I had at the beginning. H of x plus h of y minus h of x and y. This is equal to, so I saw this a moment ago. I can write this, h of y minus h of y given x. Do you think there's another way I can write that? What if I start with h of x minus h of x given y? Same way to prove that. I just substitute this by h of x plus h of x given y. And then I will end up with, excuse me, that's not right. All right?
Yeah.
That's h of y plus h of x given y, that's why. That's how the chain rule works.
Could you make a comment saying that mutual information should be symmetric because it's the same channel from both ends? So just replace x and y.
Yes. So in fact, that's my next statement. It's commutative in x and y. And the proof is here, because if I, well, for one thing, h of x and y, if I flip them around, makes no difference. And if I substitute y for x here and x for y here, it makes no difference. So there's no difference in how you calculate I of xy and I of yx. Okay, if I write, what's the mutual information between x and itself? What do you suppose that would be? Let's look up here.
H of x.
It's h of x, that's right. One way to think of that is that that's what we just proved in the example, because what we proved in the example was the mutual information between x and y, where y equals x, and we showed that that was equal to h of x. But you can also show it up here. Entropy of x plus entropy of x minus the joint entropy between x and itself. The joint entropy between x and itself is just h of x. So that's h of x plus h of x minus h of x, which is h of x. Another good one. So similarly, I of y and y is h of y. So that's just a labeling issue. Mutual information is positive. One way to show that is, we remember from one of our earlier lectures, we showed that h of y is greater than or equal to h of y given x. So in other words, any condition on an entropy is smaller than the unconditional entropy. Yes.
Can you use the distance formula, because this is dealing with h of x and y. It has the joint probabilities there. There was a German sounding name.
Yeah, the Kovac-Leibler.
Yeah, yes,
Yes.
yes.
In fact, that's the other way to show it. In fact, why don't we do that?
Is the mutual information also bounded on the other side?
Yes. What do you think it's bounded by?
One.
No. Okay. One way to think of this is look at this expression. So entropy is always positive.
Right.
So what is the, in order to make this maximum, we should make either this guy maximum or this guy minimum. What's the minimum possible value for this? 0. So entropy is positive, so this thing is maximum at 0, or excuse me, this term is minimum at 0, so the maximum possible value of mutual information is what?
H of x.
It's h of x. Or, using the other one, h of y. So in other words, 0 is less than or equal to mutual information between x and y is less than or equal to min h of x, h of y. So in a binary, if this is a binary channel, then the maximum is 1, that's right.
Right.
But that's because the maximum value of h of x in a binary channel is 1. Pardon me. Okay, that's actually a good point. If I don't know anything about, I don't have this in my notes, but if I don't know anything about x and y, what is, so I can write this, 0 less than or equal to ixy less than or equal to h of x, but h of x is less than or equal to what? What's the maximum possible value of h of x? If x is defined over the alphabet sx.
The number of characters, number of
Log
code
2,
characters.
log 2.
Yeah, log of the number of characters. Log sx, and similarly, this would be less than or equal to log sy. So therefore, we can more generally say 0 is less than or equal to mutual information between x and y, less than or equal to the minimum, excuse me, log of the minimum between, that's not sx, it's cardinality of sx and cardinality of sy. Min cardinality sx, cardinality sy. So this is where your 1 would come in.
Yeah.
If either x or y was binary, yeah, it would be 1. Okay, let's back up a second and show that it's positive. So I hand wave my way through the positivity of mutual information, but we can also show it it's positive from the Kovac-Leibler distance. So mutual information between x and y is equal to h of x plus h of y plus h of x and y, excuse me, minus h of x and y, which is equal to, if I expand all of these, this is the sum over x, p of x log 1 over p of x, plus the sum over y of p of y log 1 over p of y, minus the sum over x and y of p of x and y log 1 over p of x and